Welcome to our week one discussion for discrete mathematics. For today, our learning outcomes or our objective is to be introduced to discrete math and its scope of learning. Second one is to familiarize with the applications and fundamentals of discrete math. And lastly, to understand and solve given samples in the course module. So what are the topics that we will be discussing for today? First would be the introduction to discrete math, and followed by mathematical statements, the atomic and molecular statements, and implications like converse, contrapositive, and inverse. We begin by defining what discrete math is. So discrete math is the study of mathematical structures that are countable or otherwise distinct and separable. In this course, we will study four main topics: combinatorics, the theory of way things like combine, in particular, how to count these ways; sequences, symbolic logic, and lastly, graph theory. Erdos was considered to be the father of discrete math. Okay. A statement or a proposition is any declarative sentence which is either true or false, but not both. Okay. So when we say either true or false, but not both, we cannot have an answer that is both true and false at the same time. Okay. So just either true or false. First example is that telephone numbers in the USA have 10 digits. So that is a declarative sentence. It states a fact. The moon is made of cheese. Okay, so it states a fact. But regardless whether that is true or that is false, that is still considered as a proposition or a statement. 42 is a perfect square. So that is still a proposition, regardless whether that is true or false. But we all know in reality, 42 is not a perfect square. Even number greater than 2 can be expressed as the sum of two primes. So that is still a statement, regardless whether that is true or false. 3 plus 7 is equal to 12. That is a statement, regardless whether that is true or false. But we all know that 3 plus 7 is equal to 10 and not 12. Although we also know that the moon is not made of cheese, but still it is considered as a proposition, a statement. So let us now see the examples below, which are not considered as a proposition or a statement. So the first example that we have here is, would you like some cake? Okay, so we cannot consider this as a proposition. Why? Because it is an interrogative type of sentence. It asks a question. Okay, so you would see here a question mark. So this one is already an indication that this statement is not considered a proposition. Based from the examples that you see here above, you did not see any question mark, right? So, okay, so that is one clear indication as well that that statement might be considered a proposition. The sum of two squares. Why do you think it is not considered a statement? It is not considered a statement because there is no way for us to know whether that is true or false, because the statement itself is not complete. Okay? Although it ends with a period, but the statement itself is not complete. It does not state a fact. Okay, so there's no way of telling whether this one is true or false. The third example we have here is 1 plus 3 plus 5 plus 7 plus dot 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 plus 2n plus 1. This one is also not considered as a statement. Why? Because it contains a variable n. Okay? Unless we substitute a value, that is when we will be able to know whether that statement is true or false. The fourth example is go to your room. You would see that at the end of the sentence here, there is an exclamation mark, meaning it doesn't state a fact, right? It tells you to do something. It is a command. Therefore, there's no way of telling whether that statement is true or false. Okay? And lastly, we have 3 plus x is equal to 12. We will not be able to know if that statement is true or false because of the variable x. Unless we substitute a value to x, then that's the only time that we can consider the statement as a statement or proposition, because we can tell whether that is true or false. Let's say, for example, we substituted 6. So 3 plus 6 is equal to 12. We all know 3 plus 6 is not equal to 12, right? So therefore, we can say that the proposition or that statement is a proposition. A statement is atomic if it cannot be divided into smaller statements. Otherwise, it is called molecular. Just in chemistry, we all know that hydrogen, the elements in the periodic table are atoms, meaning we can no longer simplify or divide them into smaller particles. So that is the smallest part, right? But if we combine these atoms, we form a molecules. Okay, the same thing goes here with in discrete math. If we combine atomic statements, then we can form a molecular statement. Okay, as you can see here, you can build more complicated or molecular statements out of simpler ones using logical connectives. So these are examples of atomic statements because we cannot break down this into simpler sentences because it is already simplified. Okay, telephone numbers in the USA have 10 digits. So this is an example of an atomic statement, because if we are going to divide it into into different statements like telephone numbers, so we don't know. We cannot consider that a statement. And then if we are going to have in the USA have 10 digits, we don't know also what is in the USA that have 10 digits. So we cannot divide it anymore. So it is already in the simplest form. The moon. What about the moon? Can we tell whether that is a true or false? No, right? So what if our next sentence is made of cheese? So what is made of cheese? Does it define or does it state something for us to be able to know whether that is true or false? So of course, again, the answer is no. So therefore, these examples that we have here and also in the beginning of our lecture are examples of atomic statements and considered as propositions. Now, I've mentioned that if we want to make a molecular statement, we combine atomic statement. So how do we combine atomic statements? We have to use logical connectives. Okay, so in here, as you can see, telephone numbers in the USA have 10 digits. So that is one atomic statement. And then I added 42 is a perfect square, which we all know is again an atomic statement. So to be able to make these two atomic statement a molecular statement, I made use of a logical connective. And that logical connective is the word and. Okay, so there. Note that we can break this down into two smaller statements. The two shorter statements are connected by an and. Okay, so we can separate this because If we separate this, the one on the left is still considered as a proposition or a statement in its atomic form. And as well, this part of the statement, which is also a proposition in an atomic state. So we will be considering 5 connectives. So you would see that I highlighted and underlined it in red so that you would know the different connectives that we use. And adjacent to that, you have an example of the sentence. Okay. Sam is a man, so that is an atomic. Chris is a woman, another atomic statement. And then I combined it using a connective. And that connective is and. Sam is a man, Chris is a woman. So to be able to make it into molecular statement, I made again use of the connective or. So Sam is a man or Chris is a woman. And then we have here the connective if then. If Sam is a man, then Chris is a woman. Okay, so the logical connectives, the logical connective that we use is the if then. And then for the fourth one, we have here if and only if. Sam is a man, if and only if Chris is a woman. And the last logical connective is the word not. Sam is not a man. Okay, so there, that is a logical connective. So the first 4 are called binary connectives. Why do we call it a binary connectives? Because they connect 2 statements. While the last connective, the word not, is an example of unary connective, since it is applied to a single statement. We did not combine atomic statements here. Okay, that's why it's just used as unary connective. It is used or applied into a single statement. These molecular statements are, of course, still statements. So they must be either true or false. The absolutely key observation here is that which truth table the molecular statement achieves is completely determined by the type of connective and the truth values of the parts. We do not need to know what the parts actually say, only whether those parts are true or false. So with that connectives shown to you, we will be using these symbols. Okay, so you would see here the logical connective symbols. It's like an arrowhead pointing upward, an arrowhead pointing downward, an arrow pointing to the right, a bidirectional arrow, and then this the symbol. It's like a letter L. Okay, a stumbled letter L. Okay, so when you see this symbol, okay, and then P, it is read as not P. Okay, so not, this symbol corresponds to the logical connective not. So if you are going to read it, not P. Okay, and it is called a negation. P and then this symbol Q is read as P or Q, and it is called a disjunction. If the arrowhead is pointing upward, it is read as P and Q and called a conjunction. And then if we have an arrowhead pointing to the right, we can read it as if P then Q. And it is called an implication or conditional statement. And lastly, if you have this symbol, a bidirectional arrow, P bidirectional arrow Q is read as P if and only if Q, and it is called a biconditional statement. Okay, again, If you see the symbol, this is not. Pointing downward, it's or. Pointing upward, it's and. An arrow pointing to the right, if then. And a bidirectional arrow pointing to left and right, if and only if. Okay. So what would be the truth values for these connectives? Not P is true when P is false. So let's say, for example, you are asked to get the negation, meaning the opposite. Not raining. So what's the opposite of not raining? It's sunny, right? If it's not sunny, then it is raining. Okay. And then P or Q will be true when both are true. P and Q is true when both P and Q are true. If P then Q is true when P is false and Q is true, or both. P if and only if Q is true when P and Q are both true or both false. So these are the conditions wherein you will have a true, okay, true truth value. So later on, I will be showing more examples so that you will be able to understand what these mean. Okay, so let's start with negation. Let P be a proposition. The negation of P, denoted by this symbol, okay, is the statement it is not the case that P. Find the negation of the following statements or proposition. So our proposition here is false. So what is it? Its negation. Of course, the opposite of false is true. If our proposition is true, what is its negation? Therefore, it is false. So we just negate or we take the opposite of that condition. Okay, so let's have the first example. Today is Friday. So let us assume that this one, the proposition is true. Okay, it is true. What is the negation of this statement? The negation of this statement is today is not Friday. Okay, so that is the opposite. If we have this statement, it is not raining today, let us assume that this proposition is false. So what is the opposite of this? It is raining today. It is a matter of removing the word not and then or adding the word not, create the negation of the statement. Again, today is Friday. If we would like to take the negation, today is not Friday. If we would like to take the negation of this statement, we remove the word not. Okay, so the negation is it is raining today. Okay, you just take the opposite. The second one is conjunction. Let P and Q are propositions. The conjunction of P and Q, denoted by this symbol, P and arrowhead Q, is the proposition P and Q. The conjunction P and Q is true. Okay, it is stated here. It will have, let me just use my highlighter. P and Q is true when both P and Q are true. So let's see, where's that condition? It says here that when your P and Q are true, your P and Q are true, that is the only time that this statement would be true and is false otherwise. So as you would see, all the values here are false. Okay, so that's how it is. So that is the only time that we will have a true truth value if both our P and Q are true. So we have here a statement. It says here, today is Friday and it is raining. So let us assume that this statement is both true. Okay. So how will we make this statement follow this condition? Okay, so today is not Friday, so we are going to negate this. Today is not Friday and it is not raining. Okay, so that is for the first condition. For the second condition, false true. So we are going to make it false true. Today is not Friday and it is raining. For the third condition, true false. Today is Friday and it is not raining. Okay, so that is how we make this statement follow our proposition here. What about the disjunction? Let P and Q are propositions. The disjunction of P and Q, denoted by the symbol, is the proposition P or Q. The disjunction P or Q is false. Okay, says here, it will have a false value. Okay, when both P and Q are false. So let us locate that. P and Q are false. So P and Q, P here is false, Q here is false. That's why our disjunction P or Q is false. And is true otherwise. So as you would see, everything here is already true. Okay, so we have here a statement. Students who have taken calculus or computer science class can take this class. So let us assume that the statement is true, both true. So how can we make this statement false? So first, okay, so true, false. Students who have taken calculus, okay, students who have taken calculus but not computer science can take this class. Okay, so we have the negation here. So for this one, we're going to negate this. Students who have not taken calculus but taken computer science can take this class. Okay. How do we make the first statement? Both false. Students who have not taken calculus, neither calculus nor computer science can take this class. So that's how we take the disjunction and the negation of each statement. Now this is our only condition. For the implication if then, there are many ways. There are many ways wherein we can represent it. Okay. So let P and Q are propositions. The conditional statement if P then Q. The conditional statement if P then Q is false. So this is the condition when P is true and Q is false and true otherwise. In the conditional statement if P then Q, P is called our hypothesis, sometimes referred as antecedent or premise, and Q is called your conclusion or your consequence. So these are the different representations that we can use for implications. Okay, if P then Q, if P comma Q, P is sufficient for Q, Q if P, Q when P, Q unless not P. So these are just some of the representations of implications. So this is the truth table. It is said there that we will have false, okay, when P is true and Q is false. Where is it in the truth table? It says here that when P is true, Q is false, then the implication if P then Q is false. Okay, so a statement here, if I am elected, then I will lower taxes. So let us assume that this statement is both true. Okay, so in this one, if I am elected, then I will lower taxes. So let us assume that again, they are both true. This is your P and this is your Q. So how will we make this statement, this pattern? Okay, you have to take the negation of that. If I will not be elected, then I will not lower taxes. So you have seen that I have introduced the word not to negate the statement. From true, it now became false. Okay. Next condition, false true. If I am not elected, then I will lower taxes. What if for the third one? True and false. So that is going to be, if I am elected, then I will not lower taxes. Okay, so this is the most possible. Okay, if I am elected, then I will lower taxes. First statement, if I'm not elected, then I will not lower tax. So we have here the biconditional statement. So what would be the condition? You will only have a true. Okay, true. This will only be true when P and Q have the same truth values. So meaning, if P and Q are both false, then you have a true. If P and Q are both true, then you will have a true truth value. Okay? If not, we will have false. We would see if you have different inputs for P and Q, the answer would be false. Okay? So the challenge now here is this one. So again, this is our P. Okay, so P. And then this is our Q. So we are going to assume that our P is true. Okay. So that is the only time that you can take the flight if you bought a ticket. You can take the flight if and only if you buy a ticket, of course. So let us now make this statement, this condition, false and false. You cannot take the flight even if you bought a ticket. If you don't have the ticket, then you cannot take the flight. Again, if you cannot take the flight if you don't buy a ticket. Next would be false and true. So we will make this false while retaining this one as true. So you cannot take the flight even if you bought a ticket. What are the circumstances wherein you have a ticket but you cannot take the flight? You might have missed the flight. Maybe you came in late. You are 30 minutes late. Okay, so that's why the airplane already left. Or perhaps you are carrying with you illegal substances like illegal drugs, or you might have ammunition that is not supposed to be carried during the flight. Okay, so those are the some of the circumstances wherein even though you have the ticket, but you cannot take the flight. Okay. What about the third condition? True and false. Okay, this one. You can take the flight even you don't have a ticket. So, what do you think are some of the circumstances in that situation? The flight attendant, yes, of course, are always exempted for buying a ticket. That's a very bright idea. I love that. That's correct. You are the president. Well, you have your own airplane, by the way, like the president of the U.S. They have he has his own airplane, the Air Force One. Yes, you're the pilot. You win a free ticket. Yes, that your answers are correct. You are the owner of the airlines, of course. You're the pilot. You got it all correctly. Very good. Thank you for that response. No. Now we are going to differentiate this converse, that the shoes, contrapositive, and the inverse. The proposition if Q then P is called the converse of if P then Q. The contrapositive of if P then Q is the proposition if not Q then not P. The proposition if not P then not Q is called the inverse of if P then Q. So when two compound propositions have the same truth value, we call them equivalent. So that a conditional statement and its contrapositive are equivalent. The converse and inverse of a conditional statement are also equivalent, but neither is equivalent to the original statement. So let us take this example. The home team wins whenever it is raining. So this is our statement. Okay. The home team wins whenever it is raining. So if we are going to assume that our P, okay, so you would see the color. This is our P, and then this is our Q. If P, so you will see here the connective, if, and then. Okay, so if P, then Q. So this is if P, then Q. If it is raining, then the home team wins. So do you think that they have the same meaning? The home team wins whenever it is raining. Okay, so we have converted this statement to this if P then Q. Now, let us take the contrapositive. It says here, if not Q, then not P. So meaning, we are going to negate, okay, the statement Q first and followed by the negation of P. Okay, so you will see here the home team wins. That is our Q. If we are going to negate it, you would notice that we have introduced again the word not to negate it. If the home team does not win, then we negate this. It is not raining. Okay, so that is true because it is in the statement the home team will only win if it is raining. Okay, so if the home team does not win, then it is not raining. Next is the converse. If the home team wins, okay, if the home team wins, then it is raining. Okay, so you would see that these two have just exchanged its place, right? If the home team wins, then it is raining. And then the inverse, okay? If not P, then not Q. If it is not raining, if it is not raining, then the home team wins, does not win. Okay? So that is how we make a statement, a conditional statement, a converse, a contrapositive, and inverse. Okay? So that ends our virtual class for today. And for next week, if you would also refer to your LMS, the topic should be about sets.